The next speaker is Andrew Erwin from Rice University. Andrew is going to talk about design philosophy for creating a series elastic actuated wrist assessment exoskeleton. Please go ahead, Andrew.
Great, thank you. You can see my screen?
Yeah, it works.
Great. Hello, everyone. I'm Andrew Erwin, and this is today I'm going to be talking about some work I did as a graduate student at Rice University in the Mechatronics and Haptic Interfaces Laboratory, which is run by Dr. Marcy O'Malley. And one of the focus areas of the MAHI lab was on using robotic devices for rehabilitation after spinal cord injury. And the objective of this type of rehabilitation is to try to promote neural reorganization. But a side effect of this might be changes in biomechanics, and we hope that eventually this will all lead to functional recovery. And in my work as a PhD student, I was focused on how can we use robots to help us actually assess what is going on in this process, since there's a lot of unknowns happening between rehabilitation and end recovery. And this was well stated by this review paper back in 2016 that said, although essential for maximizing individual therapy outcomes, the use of assessment methods in routine practice is at present insufficient. This led me to create the SE-AssessWrist. It's a 2-degree of freedom device with a serial mechanism for flexion extension and radial ulnar deviation of the wrist. And the main difference between the SE-AssessWrist and other rehabilitation devices is that it has an increased range of motion while also maintaining torque output. This was accomplished by locating the motors remotely with the Bowden cable transmission and using series elastic actuation at the device on board. And when I was creating this device, in the spirit of this workshop, I'll focus on the design and hopefully relay some practical and lessons learned on how to manufacture. In the AssessWrist, I like to try to use a modular design philosophy in that I was able to break the design up in my head into different modules, where I was able to leverage that certain similarities would be replicated for each joint. In particular, for this robot, there's the flexion extension joint, the SEA module, and the RUD joint. And an important part of modules is how you connect them. And when you're in research developing such a testbed device, I found it really useful to be able to have a device that could really be easily assembled and disassembled. This wasn't necessarily commonplace with all of our devices, and I found this really useful. By using these flange mount shaft collars, you're able to really quickly detach and reattach modules. A nice feature of this approach too is that you can easily reconfigure your device to be tested in isolation. For example, here I can test the flexion extension unit in a standalone testbed. This is useful for troubleshooting the control strategies as well as verifying the design. And in fact, I used a very simple mock-up of this in my earlier work to verify the concept and learn more about the process before fabricating the components. When creating the SEA module, I was also able to learn some lessons throughout the process. The first was that trying to minimize the amount of components in the assembly was critical. In an earlier prototype, we separated the spring into multiple steps. This could create hysteresis between the spring and the next stage. So in the ultimate design, I used the solid ring as well as CNC'd this SEA so that this hub could also be integrated all into a single component. Similarly, for the pulley, it had multiple design features that leveraged the monolithic design principles, such that it had this built-in indent so that the spring rests, and when it deflects, it doesn't rub on the pulley, and also included its own built-in shaft. And compared to a previous iteration, this spring was very linear in the torque range that we were interested in, which is up to 3 Newton meters. And finally, the AssessWrist used a lot of different manufacturing techniques. We're fortunate today to be able to use things like laser cutting, 3D printing, CNC machining, and milling. And I was able to leverage all of those manufacturing processes in the design. For example, high precision components like the shafts we machined in-house, whereas the spring was CNC'd. We're also able to leverage 3D printed components to lightweight and also save costs and increase lead time, or decrease lead time. And you need to know when you're doing these things where you can incorporate these in such a way that they won't compromise the structure of your device. Okay, this was a really quick overview, and I hope you learned some lessons. And if you're interested to learn more, I refer you to these publications as well as my personal website. Thank you for your time.
Great, thanks a lot, Erwin.